This comparison of identical samples run through an HPLC highlights the difference between success and failure. In the center blue box, the peaks are sharp and distinct. On the left and right, they've collapsed into overlapping blobs. A sharp peak represents a perfect physical scenario, identical molecules traveling together, striking the finish line simultaneously. But thermodynamics works against this order. Once inside a column, natural forces begin pulling that group apart, causing the peak to stretch and flatten. Achieving high resolution requires a constant, active fight against this natural broadening. The primary weapon available to a scientist in this fight is velocity, adjusting the flow rate as it pushes the sample through the column. However, this creates a strict operational paradox. Running the liquid too slowly allows the peaks to widen, but pushing them too fast leads to the exact same failure. Solving this paradox requires zooming down to the microscopic level to observe the specific kinetic forces acting on those moving molecules. This brings us to rate theory, a model tracking the messy, dynamic reality of molecules constantly in motion inside a packed column. The first force is eddy diffusion, or the A term. Inside the column, molecules don't travel in straight lines. They must navigate a chaotic maze of packed silica particles. Some molecules find short, direct paths, while others weave through long, winding routes. Even though they started together, they arrive at the finish line at different times. Because this obstacle course exists regardless of how fast the liquid moves, eddy diffusion acts as a constant, unavoidable baseline of peak broadening. The second force is longitudinal diffusion, known as the B term. This becomes the primary enemy when the flow rate is set too low. Molecules possess a natural thermodynamic urge to slowly drift from areas of high concentration outward into empty space. If the liquid moves too slowly, the sample lingers in the column, providing enough time for molecules to spread forward and backward, widening the band. The only way to minimize this longitudinal spreading is to crank up the flow rate so the molecules spend less time diffusing inside the column. But pushing that speed leads to the final hurdle, mass transfer resistance, or the C term. To separate effectively, sample molecules must constantly hop in and out of the deep pores covering the stationary phase particles. If the main liquid stream moves too fast, the molecules floating in the center of the flow get violently swept far downstream. Meanwhile, their identical partners are temporarily left behind, stuck inside the stationary phase pores. Running the machine too fast literally rips the molecular band in half, requiring the scientists to slow down to keep the group together. Combining these three kinetic forces onto a single graph reveals the famous U-shaped Van Deemter curve. This graph plots flow rate on the x-axis against peak broadness, or HETP, on the y-axis. The exact lowest point of the U identifies the optimum velocity, the perfect sweet spot of efficiency. At this specific speed, the liquid moves fast enough to outrun longitudinal diffusion, but slow enough to allow perfect mass transfer in and out of the pores. This mathematical curve solves the flow rate paradox, establishing the ultimate physical speed limit for a traditional chromatography column. This plot shows how modern UHPLC technology breaks that traditional limit by using microscopically small particles. The green curve, representing 1.7 micrometer particles, enables much higher efficiency at higher speeds than the blue curve of 5 micrometer particles. These tiny particles flatten the right side of the curve because they minimize uneven paths and make the pores shallow enough that mass transfer happens almost instantly. Setting the flow rate is a deliberate manipulation of kinetic forces to keep a chaotic microscopic universe perfectly in line.